All right, now here I have a Venn diagram set up where again I have three sets and they all overlap. Um, and I've got regions labeled with Roman numerals. Okay, so the Roman numerals are not elements of the sets. They are the names of the different regions in the Venn diagram. Okay, so we say this is region 1, region 2, region 3, and so forth, up to region 8. Okay, so these are the Roman numerals. And we're going to use this map, this Venn diagram, to prove some statements. Here's some set theory equations. You'll see some set theory equations in the homework. You'll either have to prove them in a similar way, or you'll have to state whether they are true or false. And then you can, basically to determine that, you want to prove, which is what I'm going to show you here. Okay, so first of all, what I like to do is just break these down one side at a time. On the left side, I see that set B contains regions 2, 3, 5, and 6. Okay, so 2, 3, 5, and 6. Those are all contained in set B. Okay. Now if I look at A union C, we can determine what all regions are contained in A union C. Well, A union C is just going to be everything in A and everything in C. So it'd be 1, 2, 4, 5, and 7. So 1, 2, 4, 5, and 7. Okay, those are the regions in the union of A and C. 1, 2, 4, 5. Oh, I missed 6. 6 is also in 7 in C. We'll make that one into a 6, and we'll add 7 on at the end. There we go. So 1, 2, 4, 5, 6, and 7. So only 2 and 8 are not in there. Okay. And then if I want to find the intersection of B and A union C, which is what's on the left here. So B intersect A union C. Well, that's going to contain regions that are in the overlap of these two, that are in both, right, for an intersection. Bad looking U. There's our U. Okay. So the intersection is the regions that appear in both. Well, 2 appears in both, 5 and 6. 2, 5, and 6. Right, so that's regions 2, 5, and 6. Let's see where they are on the chart here. 2, 5, 6. So it'll be these 3 regions on the toward the middle and right. Okay, so now what we need to do is just to see if the other side, when I evaluate it and think about what regions they are, if the regions are the same. Okay, that's how we would prove this to be true. All right, so let's look at A intersect B for a minute. So A intersect B, that's going to be this teardrop, teardrop 2 and 5 are in that region. And then let's look at B intersect C. B with C, that's going to be 5 and 6. And then if I look at the union of those two sets, it's all the regions that appear in one or the other or both, right? So that means that A intersect B union with B intersect C is going to be, it's going to include region 2, region 5, and region 6. 2, 5, 6. Does that match up with what we had before? 2, 5, 6. Yep, sure does. So that's proof enough. We could just say that both sets contain the regions, contain only the regions, should specify that, 2, 5, and 6. Oops. I comes after the V and 6. There it is. Okay. So yes, for sure, our equation is true and is now proven. Okay, because the regions are the same on both sides. So if the regions on the Venn diagram are the same, it just means the elements that these sets contain are the same, right? So on the left here, this set contains the same elements as the set on the right because they have equivalent regions on the Venn diagram. All right. Okay. And of course, you could do some other weird things here as well. But the main idea is you can identify what regions on the graph are contained in each expression. Just by kind of breaking it down one piece at a time and then getting either their unions or their intersections based upon that.